Chapter 5, Water for Life, Part 1. In this first lecture, we'll be talking about the unique properties of water, the role of hydrogen bonding, water usage, and water issues. Some of the questions we want to ask in this chapter are, do you know where your drinking water comes from? Do you know if your drinking water is safe to drink? How would you know? Well, it looks pretty obvious if your drinking water was as disgusting as this that you would know. But very often your water could look like the picture on the left, just perfectly clear, and it may contain contaminants. So we'll learn about the chemistry of water and how to understand the water reports you may receive from your municipal water agency. There is an optional lecture activity, and it's an overview of polarity. Polarity is when the atoms in a molecule share their electrons unevenly, and it's very important to understand the concept in order to understand why water behaves the way it does. I will cover the same information in this lecture as well, but it would be good reinforcement if you're able to view it. So, to review how we could potentially represent water, we have the Lewis structures here, these first two representations. Then we have a representation actually showing the shape of water, and water is a bent molecule due to the two lone pairs on oxygen. They're slightly more repulsive. You don't have to worry about the specific 104.5 degrees angle as long as you know that molecules with 4 electron groups around them have about 109.5 degree angles. That's fine. And then of course we have our space filling model of water. Electronegativity is a quality, an innate quality for an atom to draw electrons to itself. Part of that quality is determined by the number of protons in the element. It's also going to be determined by how many electrons the element has and how far away those electrons are from the nucleus. We're going to be looking at just the main group elements and ignoring the transition metal elements for now. We won't be calculating electronegativities. The values for electronegativities will always be given, or you can look them up. There may be slightly different values of electronegativity depending on the source of information you're using, but the overall trend remains the same. Fluorine is the most electronegative element and usually will have a electronegativity value of 4.0. The noble gases have 0 electronegativity because they are completely stable. They have their octet without having to share any electrons with anyone else. They're in group 8. They have 8 electrons around them. Since the number of valence electrons primarily determines reactivity, and they have a complete octet, noble gases are not reactive. Fluorine, which is very close, and chlorine as well, very close to having their octet, is very electronegative. The alkali metals, on the other hand, the way they could form their octet, perhaps faster than trying to gain 7 electrons, would be just to lose 1 electron. And bam, all of a sudden they would have their octet or duet. So the trend is the electronegativity increases going left to right towards fluorine. And then as you get bigger and bigger, as you get larger and larger atoms going down the periodic table, electronegativity decreases. You can think of it as electrons essentially being further away or shielding the nucleus, and therefore the nucleus is not able to draw in electrons as much. So fluorine is our most electronegative in the upper right-hand corner, and you would think that down here in the lower left-hand corner would be our least electronegative elements. So why is electronegativity important? Well, when you have a difference in electronegativity or electron pulling power between atoms in a molecule, you obtain an uneven distribution of electrons. What does that mean? Well, when you have an uneven distribution of electrons, you're going to have a polar bond or a overall polar molecule. You could see here, because oxygen has such a strong pull on those electrons in that molecule, they tend to stay around the oxygen atom for the majority of the time, giving oxygen a slightly negative partial charge. And that's what this little symbol here means. It is a Greek delta, a lowercase d, and it's referring to partial. We usually draw just a negative or a positive or two positive without that symbol when we're talking about ions. But when we're talking about covalent molecules and showing the polarity in covalent molecules, we use a delta symbol. So to summarize, a polar covalent bond is a covalent bond which the electrons are not equally shared. There is an atom in that molecule that has greater electronegativity than the others and pulls the electrons towards it. Now let's look at a nonpolar covalent bond. Something that has a nonpolar covalent bond, either the atoms have such a small difference in electronegativity that they essentially act as if there is no difference, or you have the same atom. Obviously, if you have the same atom, there's no difference in electronegativity, so they have equal pull on the electrons. We can also look at the electronegativity of ionic compounds. That difference will always be very large. And sometimes we say, okay, if there's a difference in electronegativity more than 1.5, the compound is ionic. I prefer, at this level of chemistry, just to think of metals and nonmetals forming ionic bonds. We won't be doing any of these electronegativity calculations for ionic compounds. So, when you have these partial charges, what do we know about electrical charges that are opposite, say negative and positive? Well, they attract. So if you have these molecules that have partial negative and positive charges on them, they attract other molecules with positive and negative charges. The attractions between entire molecules, not within the molecule, is known as intermolecular force, abbreviated IMF. It's very different from the attractions in covalent or ionic bond. For example, it may require approximately 400 kilojoules per mole to break a covalent bond, while disrupting an intermolecular force, an attraction between molecules, takes much less energy, between 1 to 15 kilojoules per mole. And I like to use the term disrupt or pull apart or anything other than break. Break I like to reserve for very strong covalent bonds or ionic electrostatic attractions. You may see people referring to breaking hydrogen bonds, but I feel it improves the clarity of the discussion if we refer to disrupting hydrogen bonds and breaking covalent bonds. So here we see the difference. This is a covalent bond between a hydrogen and a chlorine atom. It's very strong. It's known as an intramolecular force, versus the attraction between two molecules is an intermolecular attraction and is much weaker. One type of intermolecular force is called hydrogen bonding. As I mentioned before, it's much weaker. Any intermolecular force is much weaker than the force within a molecule, intramolecular force. Instead of single lines showing the bonds between atoms, we use dashes to show that there is some type of attraction going on between the molecules, but not as strong as covalent bonds. Now, these intermolecular forces can only occur, this hydrogen bonding can only occur, this specific type of intermolecular force, if an atom has a fluorine, oxygen, or nitrogen, referred to as the Fon atoms. That fluorine, oxygen, or nitrogen has to have a hydrogen attached to it. You would then draw a dashed line from that hydrogen to a lone pair of electrons on another fluorine, oxygen, or nitrogen. Let's take a look at how we would draw the hydrogen bonding between molecules of water. So here we have an oxygen attached to a hydrogen. So one of our Fon atoms. That hydrogen has a partial positive charge on it. Because of the high electronegativity of water, the electrons are drawn to the hydrogen and centered on the oxygen. That partial positive on the hydrogen is attracted to a partial negative on another oxygen atom. And so we draw a dashed line to the lone pair on the oxygen atom. Let's take a look at an animation of water-hydrogen bonding. Here we have a cube filled with water molecules. Now I'm going to animate them so we could see how a solution of water may look like on the molecular level. The molecules will be moving very quickly, not as quickly as they might at room temperature, but it'll give you a sense on what it could look like, or it should help you at least conceptualize what's going on when water-hydrogen bonds. So in a liquid, molecules are in a constant state of motion, kind of bumping into each other. If it was a solid, they'd be stationary and just vibrating slightly, depending on the temperature of the solid. So now you have the dashed lines showing the hydrogen bonds between the white hydrogen atoms and the negative, partial negative charged on the oxygen atoms. Thinker buddy question. Numbers 1 through 4 are used to identify 4 different elements. Based on trends within the periodic table, which element is expected to have the greatest tendency to attract bonded electrons? Is it element number 1 in the upper left-hand corner of the periodic table? Element number 3 in the lower left-hand corner of the periodic table? Element 2 in the upper right-hand corner of the periodic table? Or element 4 lower down in the right-hand side of the periodic table? Element 2 has the highest attractive ability in terms of drawing electrons to itself. Remember, our electronegativity trend increases going left to right and also increases going from bottom to the top of the periodic table. Thinker buddy question. This diagram represents water molecules arranged in the liquid state. To what kind of bonding forces does the arrow point? And if you look, it's showing hydrogen bonding between a number of different water molecules, and the arrow is pointing right in between a hydrogen and oxygen atom within the same molecule. Is it A, a covalent bond, a type of intramolecular force? B, a covalent bond, a type of intermolecular force? C, is it pointing to a hydrogen bond, a intramolecular force? Or D, a hydrogen bond, an intermolecular force? as it's pointing to a region within one molecule, not between two molecules. We're talking about a covalent bond, which is an intramolecular force. Let's take a look at water use and the issues facing global populations. So we need water for almost everything. To produce food needs a significant amount of water. Beef is one of the highest energy and resource intensive animals to raise. If you want to be more sustainable and environmentally responsible, you'll try to limit your intake of beef as much as possible. It's also much better for you health-wise. Not only is it important for food, but it's used for almost anything in our day-to-day lives. A water footprint just refers to how much water is needed to make that item. A cotton t-shirt, 2,700 liters of water. So if there's roughly 4 liters in a gallon, we're talking about 700 gallons of water. A significant amount of water. We need to keep that in mind as far as how we reuse and recycle materials and how much water is needed to produce those materials. This graph here just indicates the water footprint for different countries, with red being agricultural goods, yellow industrial, and green domestic. There's not too much difference between these various countries in terms of domestic water consumption. China and India much less than Japan, as well as Pakistan and Indonesia are more on the order of China and India. The US is one of the largest domestic water consumers. Significant amount of water used for agricultural goods. That is the largest use of water. And US has the largest use of water for industrial goods out of any country in this graph. Now, where does potable water come from? Water that we're able to drink. This picture here is showing a globe that looks kind of sandy colored with just faint outlines of the different countries. And there's a drop of water sitting on North America, just filling up maybe about 3% of the volume of the globe. So a very tiny amount of water on the earth is actual drinking water, water that humans can consume. The majority of this water is in the ice caps and glaciers, with lakes and rivers and reservoirs being a small fraction of that. And that overall is about 2.4%. Groundwater is the remainder of our potable water, roughly 6%. This would be water that we pump from wells. This water is not necessarily distributed evenly around the world. The populations that have access to safe drinking water tend to be industrialized nations. It also depends on climate. We see a lot of green in the northern hemisphere, almost all of Europe, Asia, the United States. Much less percentage of the population has access in the southern hemisphere, excluding Australia and New Zealand. And the most water scarce regions are in Africa. Thinker buddy question. Most of the Earth's freshwater supply is found in A, the oceans, B, plant material, C, as clouds in the atmosphere, D, in ice caps, glaciers, and groundwater. Most of our fresh water is in ice caps, glaciers, and groundwater. The majority of salt water is in the ocean, so 97% of the water that's not drinkable is in the oceans. This ends the first part of Chapter 5.